In this video, I'd like to help you analyze the energy and power output of the motor in a Toyota Prius. We talked about a Prius in a previous example problem when it was racing the Tesla and lost badly. I looked up online to find out that a Prius has a curb weight of around 3,000 pounds empty. So I figured if it's full of gas and a few people, its mass is around 1,500 kilograms. You should be getting better at converting between kilograms, mass in kilograms, and weight in pounds. And we found that the car accelerates from 0 to 60 miles per hour in a time of 10 seconds. I'd like to use this speeding up phase to estimate the power output of the motor in the Prius. At what rate does the motor in the Prius have to generate energy in order to accomplish this task? So we can look at this from the perspective of the work kinetic energy theorem. The total work done on the Prius is equal to its change in kinetic energy. On the left-hand side, what things do work on the Prius? Well, the motor and the transmission harvest chemical energy in the fuel and from the batteries and convert that into a force which is exerted backwards on the roadway, and by Newton's third law, this generates a force forward on the Prius. All of that is sort of immaterial because the energy to make all of this happen comes from the fuel and is harvested by the motor and transmission. So it must be that the Prius motor adds energy to the system. I'm going to say that has to be plus. And if we assume that, at least to start, there's no friction, and all of this is happening on a level surface, that's the only thing that's adding energy to the Prius, just the motor. Gravity's not taking any energy or giving any energy because the Prius isn't going uphill or downhill. There's no change in potential energy. There's no springs involved. And true enough, there is some friction, but at this stage of the game, we don't have any way to account for it, so we'll assume in the beginning that the work done by friction is equal to 0. It's probably not true, and in fact in the second part of this problem we can even verify it's not true and get an estimate for what it is. But for now, let's say that there's no friction to slow the Prius down as it's accelerating from 0 to 60, as unrealistic as that is. If that's the case, then the only thing that does work on the Prius is the motor. And the energy that the motor adds to the Prius is realized in a change in kinetic energy for the Prius. And the way you find the change in kinetic energy always is the final kinetic energy minus the initial kinetic energy. And this simplifies a little bit for us because the initial kinetic energy is 0 since it starts from rest. By the way, in order to calculate the final kinetic energy, we're going to need 1/2 mv squared, but in SI units. So miles per hour won't do. We're going to have to convert this 60 miles per hour into meters per second. You're probably getting pretty good at that, or you can look back at some previous work, but I think you get 26.8 meters per second for 60 miles per hour. So great. You're in a position now to be able to calculate the final kinetic energy, which also happens to be equal to the work, the energy added to the Prius by the motor, if we ignore friction. All right, so you plug in the numbers and let me know what you get. 1/2 times m times v squared, but use 26.8. I get 540,000 joules. And it's definitely plus because the final is greater than the initial. The initial, in fact, is 0. If you wanted to write that in scientific notation, that would be 5.4 times 10 to the 5th joules. it's always good to practice scientific notation and rounding a little bit along the way. So 5 because we got 1, 2, 3, 4, 5. Great. So what's the power output of the Prius motor? To find the power output, you have to divide the work done by the motor by the time interval that it took to do that work. The work will be in joules, the time interval will be in seconds, so the power will come out in joules per second, which is a watt. So we got everything we need. We have 540,000 joules as the work. We have 10 seconds as the time. So the power is 540,000 divided by 10. Pretty easy. That's 54,000 watts. $54 kilowatts. Now, we can put that into a little better perspective with the conversion that we know from the book, that 746 watts is equal to 1 horsepower, a common unit of energy in the English system. So if you want to calculate the power output in horsepower, you have to divide this by 746. And if you do that, I get something like 72 horsepower. So the Prius motor, at a minimum, has to have a power output of around 70 horsepower in order to accelerate the 1,500 kilogram Prius from 0 to 60 in 10 seconds. Ignoring friction, of course. So that's all well and good, but from the slowing down experiment, it's interesting. We can estimate friction. We can estimate the friction because, well, here's the experiment. My wife has a Prius. I accelerated it up to 60 miles per hour, and then I let it coast by taking my feet off the accelerator to 40 miles per hour, and I figured out it took around 30 seconds for that to happen. So when I take my foot off the accelerator, I remove the power input of the motor, and the only reason it slows down is because of frictional losses. Energy is lost to friction, and the Prius slows down. So we can calculate the amount of energy that is lost to friction in this slowing experiment, and we can also calculate the rate at which energy is lost to friction. So let's do that. We can do it in the same way we did before. We can start with the idea that the total work done on the Prius is equal to its change in kinetic energy, but in this case, there's no motor. The only thing that's doing work is friction, which we at first said was 0. And this probably should come out minus because friction will sap energy from the system. Let's see. Well, we calculate the change in kinetic energy in the usual way. The final kinetic energy minus the initial kinetic energy. The final kinetic energy is the 40 mile per hour kinetic energy. The initial kinetic energy is the kinetic energy it has at 60 miles per hour. You can see the initial is greater than the final. So their difference, subtracted this way, is going to be negative. So I'd encourage you to pause the video here and see if you can't calculate the final kinetic energy using 40 miles per hour, but you'll have to convert that to meters per second, and the initial kinetic energy using 60 miles per hour. As a matter of fact, I deleted that, so you already have that. And subtract them, and let me know what you get. Well, I'll let you know what I get. I get minus 300,000 joules. And if you put that in scientific notation, it's minus 3.0 times 10 to the 5th joules. That's all well and good, but more important is the rate at which energy is sapped from the Prius. So we can calculate the power, the rate that friction saps energy from the system. If we just do its absolute value, well, we'll just keep the minus sign here. So we got the work done by the frictional losses divided by the time interval it took to do that work. That will be minus 300,000 joules divided by 30 seconds is how long this took. So the power rating, the power at which, the rate at which energy is lost to friction is minus 10,000 watts, or minus 10 kilowatts. And if you convert that into horsepower using the formula that we had before, that 746 watts is 1 horsepower, I think you end up with minus 13 horsepower. So I hope you're verifying these calculations along the way, being a bit more active rather than passive. So what does that mean about our estimate before of the Prius motor needing to have an output of 72 horsepower? So before, we decided that the motor had to have a power output of about 72 horsepower. But that was ignoring friction. If we just say, as an estimate, that the rate at which friction saps energy from the system is always around minus 13 horsepower, then the motor additionally has to overcome that. So the Prius motor actually has to be a bit more powerful. In other words, in addition to providing the energy to speed the Prius up from 0 to 60, it has to provide the energy to overcome friction. So that means the Prius motor has to be a little more powerful than we originally thought. So I'm estimating 85 horsepower. So to reiterate, we used energy principles to first calculate how much work was done to accelerate the Prius from 0 to 60 miles per hour. And then we figured the power required to do that in 10 seconds. And we got 72 horsepower. Then we looked at a subsequent experiment where we watched the Prius slow from 60 to 40 miles per hour in 30 seconds because of friction. And analyzing things in the same way, we figured that friction saps energy from the car at the rate of around 13 horsepower. So combining the accelerating result and the coasting experiment, we can estimate more accurately what must be the power output of the Prius motor. And we get somewhere around 85 horsepower.